Let's look at 2.6. So if we are looking at 2.6, we're going to do numbers 42, 48, and 50. And then we're going to do some from 2.8. So first, number 42 is the limit as x goes to infinity of the natural log of 2 plus x minus the natural log of 1 plus x. And so first thing we're going to do is we notice that the natural log of a minus the natural log of b is the natural log of a over b. So that means I can rewrite this as the natural log of 2 plus x over 1 plus x. Okay, so with the natural log. But then I remember that as long as your function is continuous, you can let the limit pass through. So this is really the natural log of the limit as x goes to infinity of 2 plus x over 1 plus x. So limit can pass through a continuous function. So we let that limit pass through the natural log, and it goes on the inside of natural log and gives me this. But then I think I can rewrite that limit in a similar way to what we have done before. And I can rewrite that if I multiply it on the inside by 1 over x, that 1 over the highest power. It should be clear that you get 2 over x plus 1 and 1 over x plus 1. So now if you actually let the limit go to infinity, this goes to 0 and this goes to 0. So this is the natural log of 1, which you know the natural log of 1 is 0. So number 42, all of this is just a fancy way of writing 0. So that's 42. Let's look at 48. So that problem was all about changing the form. If we look at 48, we have 2x squared plus 1 over 3x squared plus 2x minus 1. They ask us to find the horizontal and vertical asymptotes. So the horizontal asymptotes, for that, we're just going to check the limit as x goes out to positive and negative infinity. So as we go out to positive infinity for this thing, I think it should be clear that we multiply it by 1 over the highest power. So that's going to give us the limit as x goes to infinity of 2 plus 1 over x squared, 3 plus 2 over x minus 1 over x squared. And now if we let x go to infinity, these terms go to 0. And you're just left with 2/3. And I think it should be clear that if you either go from positive or negative infinity, you're going to get the same number. If you need to check, you can also verify that this limit is also 2/3. So note, this limit is also going to end up being 2/3. So f of x has a horizontal asymptote at y is equal to 2/3. Well then, for the vertical asymptote, we just set the denominator equal to 0. So I have my denominator equal to 0. I want to factor that sucker. And so I know I'm going to have a 3x and a x. And I want to get a middle term of 2. So I'm going to let this be -1 and this be +1. And I think you can verify that if you multiply this out, you get that trinomial. So in other words, this is 0 or this is 0, which means -1 and 1/3 are possible vertical asymptotes. And since they're never going to cancel out with any term on top, these are both vertical asymptotes. So f of x has vertical asymptotes at x is equal to -1 and x is equal to 1/3. 48, so now let's try 50. Second verse, same as the first. if my function is 1 plus x to the fourth over x squared minus x to the fourth, well then, for a horizontal asymptote, we're really looking for what happens in the long run. So we take the limit as x goes out to infinity of this thing. So I guess I'm going to multiply by 1 over the highest power on top and bottom. And that just gives me a limit as x goes out to infinity of 1 over x to the fourth plus 1 and 1 over x squared minus 1. I think it's clear if we let x go to infinity that these terms go to 0 and you get negative 1. It should also be clear that if you go to positive or negative infinity, they're always to an even power, so it's not going to make a difference. So this thing, f of x, has a horizontal asymptote at y is equal to negative 1. So that's my original function. If you want to make it clear, I can call that f of x. For a vertical asymptote, we are just going to take the denominator and set it equal to 0. So you get this. And the reason we like things set equal to 0 is because we can factor. So if I factor, I get this, which means that equals 0 or this equals 0, which means x equals plus or minus 1, and it equals 0. And since this cannot factor nicely, these are never going to be common terms with the numerator. So f of x has vertical asymptotes, they're not going to be holes, at 0, negative 1, and 1. All right. Well, now we move on to 2.8, and we're doing number 2 on 2.8. So 2.8, number 2. Why do I have a headache? Okay. 2.8, number 2. Sorry, I'm scrolling. Number 2 is, it's a little graph type question. And here is what it says. It says, if this is our graph, it wants to estimate the value of the derivative at our points. So if I crop, I'm going to get this and this and this. So we know that the derivative is the same as the slope of the tangent line. So it looks like at 0, if that is my tangent line, it looks like the slope is approximately 3 over 1. So I'd say that that's approximately 3. At 1, it should be pretty clear that the derivative looks like it's 0. At 2, looks like we're going like that. At 2, it looks like it's about negative 1. Why? Because this is, if this is my tangent line, oh man, that's not quite right. Let me make that a little nicer. So this is my tangent line. So if that's my tangent line, it looks like this and this are the same, so it looks like it's negative 1. And then if I go at 3, so here's 1, 2, 3. So if I look at 3, I draw a tangent line here. It looks like it's about what? Those look like, it looks like this is 2. It looks like this is just about 2 as well. So it still looks like it's a little more negative, yes? So we would expect here it's even, actually no, it's a little smaller. Boop, boop, boop. So here it's a little less than 1. So maybe this is about something like negative 0.8 or something like that. It's a little less than 1 because this is 2 and this looks like it's about 80% of that or 90% of that. Okay. At 4, let's see, 1, 2, 3, so that's 3. Oh no. So 3 was here. So 1, 2, 3, 4 is right here. Do you see that it's got to be negative, but it's a smaller negative? So maybe that's like negative 0.7. And then at 5, it looks like it's 0 again. And then at 6, it looks like it's a small positive. Maybe something like 0.1. And then here, it's even a little bit more positive. So maybe it's like a 0.2. Just something like that, right? Okay, so that's 2. If we look at something like 4, which is a good one, it's wanting us to take this picture and see if from the picture we can't draw the graph of the derivative. So let's start from here. Let's use this photo. Let's crop. Here's 4. Boom. So if this is our derivative, I guess when we're drawing the derivative, we always start with the derivative is equal to 0. So it's 0 here because I have a horizontal tangent line. It's 0 there and there because I have horizontal tangent lines. So I think those would be 3 points on the graph of the derivative. But then if I move just a little bit to the left, this looks like a small negative slope. This is an even bigger negative slope. So I think as I go out this way, it's going to be even more and more negative. Over here, it looks like I have a small positive and then a bigger positive. And the biggest positive looks like it's going to be right here in the middle. So I think my slopes go up, something like that. But then notice they're positive, but they start to get smaller and smaller and work their way back to 0. So it looks like that is going to be what this graph looks like. But then to the right of the 0, it's small negative, where again, right here in the middle, looks like it's going to be the most negative it ever is. So maybe right about here is the most negative it ever is. And then it's got to come back up this way to a smaller negative until it's 0 again. And then it goes small positive, bigger positive, bigger positive. So it looks like it just does that. So notice what we've created. We took the derivative of a 4th degree, and it looks like we got something that kind of looks like a 3rd degree polynomial, and we would expect that. Cool. All right, that's number 4. Then we look at number 6. So number 6 is the same sort of deal. We're just drawing pictures. Bloop, bloop. Okay, so here's 6. Use the photo, crop, boop, boop, boop. Okay, so if this is 6, I want to draw this derivative. Again, when you're drawing derivatives, let's start where it's 0. So it looks like the derivative is 0 if I draw a mini tangent here. Then as I go to the left, it's a, what is this? Small positive, bigger positive. The biggest positive it ever is, looks like maybe it's right about there. So that's the biggest positive it ever is. Maybe right about here is the biggest positive ever it is. But then it goes, at some point, it starts to turn back towards 0. But then over here, it's smaller positive, smaller positive, smaller positive, and it looks like it goes back towards 0. But it maybe never gets there, right? So that's 0, and it looks like over here, I'm gonna have a small positive, small negative, small negative, small negative. The biggest negative is about right here. Notice how this is nice and symmetric. And then it gets smaller negative, goes back to 0, to where it looks like it's gonna do something like that, right? Okay, so that's 6. We're almost done. I've